All right, let's settle in. We got pizzas, beer. There's more than enough, I think, at the back. So, a few more people coming in. Should I use that one? Be more mobile. Am I audible? I guess so. Yeah. All right, welcome. We have a few more people coming. We chose a perfect day where there's a concert and all the traffic. So we planned it bang on on the right date, right time. Sorry about that. Sorry about all the confusion around registration. So the machine that is at the entrance of the building we booked, the registration machine is broken. So but anyways, we're here, and thank you all for coming. I know it's late, so really appreciate each one of you coming here, spending the evening here. Hopefully it's worthwhile. For those of you coming from outside Google, there's a whole lot of gRPC team members here. Please mingle with them, ask them, arm twist them, ask questions, ask for your stuff that doesn't work. Please raise your voices and be loud, and this is your chance to interact directly with them. All the gRPC team members, please raise your hand, just so that people know. Yeah, so there's a whole lot here, right? So it's it's clear we've shown up in our strength here. So this is exchange emails, and I just heard like, hey, C++ doesn't have good documentation, so please catch people. So with that, I guess my name is Varun. I'm the product guy on gRPC. Jayant here runs the engineering team. So overall questions on across languages, what are we doing? Please talk to Jayant. And we have 3 sessions today. We have the first one from Vijay and Jan on performance, which is an update on what we've been up to on performance, how is it helping us, and a bit of where we're going next with it. And then Eric from YikYak. He'll tell you a lot more about what is it and where they're taking it. It's a social networking app based in SF, pivoted around location, and they're moving their stacks to gRPC and Go and all their story around it. And then Benoit from Arista is there at the back, and how Arista is using gRPC for streaming telemetry, what options they evaluated, what they found good and bad in it. Okay, so that's the high-level agenda for today. And with that, we will get started. We will be recording the presentations, the 3 presentations, and they'll be available afterwards to view. Awesome. Any logistical questions? Washrooms are outside. Pizza beer is here, so I don't think there should be any. Cool. Should we get started? Awesome. With that, Vijay.
Thanks. Thanks, Ryan. I'm Vijay and Jen. The 2 of us lead the performance measurement. And do I need this? Is this? Oh yeah, okay, for the recording. Cool. Recording. Yeah, sure. Okay, so the 2 of us lead the performance measurement and dashboarding of efforts of gRPC. I focus primarily on the C++ side, and Jan is, in terms of development, is focused on the wrap languages. So in particular C#, as well as many other issues related to releases and distributions of gRPC. And so what we wanted to talk about today, to kick off today's meetup, was a little bit about how we actually measure performance of gRPC and make sure that things go well. This is something that we've made sort of a first-class citizen of actually making sure that we're continuously measuring performance and that we're making sure that things don't fall apart. And when they do fall apart, we try to make sure that we can identify the fact that it has. Because again, one of our things here is to try to make something that actually provides a high speed of delivery of RPCs. Of course, at any point, feel free to interrupt with questions, and either Jan or I will be glad to answer during or after. Just to give a little bit of overview, since I'm the first talk today, many of you have already got some experience with gRPC, but I wanted to actually give you a little bit of the backstory of gRPC. The history of RPC systems at Google comes through 4 generations of internal RPC systems, all of which were called stubby, 1 through 4. No big surprises there. Now, the thing with RPC systems at Google is they're everything. They're everywhere. All production systems and applications that are run here, are built using RPCs. There's over what's it, 10 is that 10 trillion 10 billion RPCs 10 billion RPCs per second fleet wide. Sorry, we weren't up to 10 to 100 yet, just 10 to 10. But that's fleet wide across the system. That's what's being hitting on stubby RPC systems throughout the system. So this is something that's been going on. So if you add that up over days, it's like 10 to the 14 and so forth. Over years, it's lots. Is the point. And so in order to support all the production systems inside Google, Stubby has APIs that are for C++, Java, Python, and Go. Those are essentially the production languages that applications at Google are written in. Now, when we put all these together, though, it turns out that Stubby is something that isn't something that we could release to the open source community. And it was something that was very important to us as part of the cloud efforts and so forth to release something to the open source community. Stubby is not suitable for open source community, not just because of the tight coupling with internal tools and monitoring systems and so forth, but also because there's a limited number of languages that are supported compared to the broader set of languages that need to be used in the outside world. So the idea behind gRPC then is to produce a system that is sufficiently capable of being released to the open source world, while at the same time utilizing the scalability, performance, and API lessons of Stubby, of the 4 generations of Stubby, I should say. Okay. So part of this then comes back to what are we doing on the performance testing side, and how are we going about doing this? Everything, again, at Google Google's famous for this. I'm not deploying any trade secrets here. Google is well known for doing a lot of test-driven development. Is that that's the way that things go. That you have specifications, and that you make sure that your program meets the specifications. Very often, you write those tests before you write the programs. It's in many regards something similar with gRPC. Every time that a pull request is sent into the core gRPC repository and sent for testing, that triggers 11,000 tests across 8 different languages, 4 operating systems, 7 compilers. Okay, so this is just basically every line of code gets tested a lot. Is the important point here, hopefully. So that's the primary purpose of all that testing, is to make sure that the system maintains proper functionality and security. Okay, we want to make sure that all the assertions and invariants that we're expecting to be true actually are true. We want to make sure that we don't leak PII and so forth. So so it's well integrated with all the security systems that are being used, authentication, encryption, and so forth. And there's also many tests because of the fact that we support so many languages and different APIs. There's also tests in place to make sure that there's interoperability across the different platforms that are supported. So those are also part of it. So this is the basic structure of how code actually gets put into gRPC, but it turns out that that's also not a bad strategy for how to deal with performance. It turns out that we feel that test-driven development is also a useful strategy for performance measurement, because the functionality of a working system isn't just, does it do the functions that are expected of it, does it support the methods that you're expecting, but also how efficiently does it do those. Okay? So again, just as with every core pull request triggering 11,000 functionality tests, it also triggers performance smoke tests. I wrote it as performance smoke test, but there's actually many different tests that get run that actually measure performance. So every single pull request that gets sent in also triggers performance smoke tests. Then beyond that, we also make sure that we're visually tracking the performance of the master release, or master version of gRPC at the head of the Git repository continuously, so that way we can monitor it. When I say continuously, the tests are run every hour. Okay, the tests take 40 minutes, so we may as well just say continuously. When I say it's run every hour and it takes 40 minutes, so yeah, the machines get 20 minutes of rest in between, I guess. To make sure the JIT compiler's working, I guess. I don't know. But basically, we're running as close to continuously as you'd want to. I guess we're leaving that space in, and so we can add in some more performance tests later. But so by visually monitoring the current performance, this gives us the capability to actually detect regressions very quickly. Did we break something? Did we make something slower? Well, first of all, did we break something? All of a sudden, if we see that the test stopped running, that means that something bad has happened. So we can actually go back and revert that change quickly. Additionally, we could see that did we slow things down? So do we have a performance regression? That's another thing that we can do, which are, obviously they can be a little more complicated because sometimes a performance regression in one part of the system happened because you did something to improve the performance in a different part of the system. And it could be that you happen to be monitoring the part that slowed down, not the part that sped up. And so there are questions that arise at that point. How do we get out of this situation? Again, the basic idea, though, is we get out of the situation the same way we get out of any other breakage. Fix it or revert it. Those are the two choices. Okay. So that's the idea there. Additionally, all of our testing for gRPC is built using gRPC. So gRPC is the platform for actually driving the gRPC performance tests. The performance test machines themselves, the scenarios under test, are gRPC servers, and they actually run gRPC. They accept a gRPC command from a driver, which then in turn tells them to configure themselves as either a gRPC performance client, performance testing client, or a performance testing server, which we'll go into. The idea behind this, again, was to exploit the fact that gRPC is highly interoperable, and this allows us to actually do things such as configure our systems using protobufs rather than command line arguments, so that we can configure them the same exact way across all platforms, Windows, iOS, Mac, and Linux, as well as all program languages choices. Okay. So a little about our framework. As I said before, in our gRPC performance testing framework, we always have some machine that happens to be in our Jenkins testing infrastructure that runs as the driver, which then kickstarts the other machines. So we have a couple of worker machines, which are dedicated machines. They can be of various sizes. You have 1-core, 8-core, and 32-core tests as appropriate. This shows there being 2 workers, but in practice, all of our tests actually use 3 workers. In practice, we have what happens then is the driver sends an RPC message to one of the backend workers that says start running as a client program or start running as a server program. Okay, so that's the important thing at that point. We always do our tests such that we have 2 clients and 1 server so that we know we're not client limited. We can push our servers harder by making sure that we're not client limited. As it turns out, clients tend to burn a little more CPU than servers anyway. So that was the important thing there. So we push our machines to be, I believe, all or most of our tests are 2 clients and 1 server. Then what those then start doing is that the machine that's set up as a test client will start sending RPCs to the test server to benchmark them. So in a continuous loop of ping pongs, it could be 1 loop or it could be multiple parallel loops of ping pongs across different channels and with many RPCs outstanding in parallel at a time as well. Okay, so this is the basic structure of gRPC Performance Testing Framework. If you ever see our GitHub on any of our pull requests, you can see that we have performance tests that are run and that are linked from there, and then you can see that as well as the fact that we have a dashboard that we'll talk about. This is the structure, though, of how all of our performance testing tools look. This works regardless of the language, regardless of the platform. Asterisk. For any of you that are using the PHP API, unfortunately, that's one that we're not testing right now because of the fact that the PHP API does not support server mode, and in order to run in this configuration, you have to be able to support a server. But besides that, all the other language support that gRPC has will have performance testing run in exactly this fashion. Regardless of the language, though, the workers speak the same API, and the API is based on protobufs. So that way they'll be told what to do or what to behave as, and this makes it very easy to do interrupt testing as a result. Okay, so that is actually something that happens on every test as well. Every test in master goes through interrupt testing in particular. Okay, here's the current status of the gRPC performance testing system. That setup that I described earlier is actually set up in GCE as separate instances to run the benchmark clients and servers. Then we have a dashboard that has 7 languages that are out there. I didn't provide a link here because you can't click here, but if you ever just do Google search for gRPC performance dashboard, the first hit is the issue that describes this in GitHub, and the first link on that page is the actual performance dashboard. Okay, so the dashboard supports 7 languages. And shows them against, it has different frameworks, but some of them show the different languages compared to each other. So for example, this one shows the round-trip secure Unary latency in different languages. That's measured in microseconds, starting with a baseline of this is netperf. So this is sort of the best you could do for just actually, it's actually better than the best you can do because that netperf is sort of a streaming ping pong, whereas what we're talking about here is unary ping pongs. But basically, so that purple is the netperf. Then I think here is, yeah, color match it. You get like the C++ latency. For unary, it's about 100 microseconds more than netperf on this in this configuration. For streaming, it's about 40 microseconds more than netperf. A couple of different languages are all clustered together here. I guess Go, Java, and C#. Are all sort of clustered around each other. Then Ruby, Node, and Python are a little higher up there. So these are, so you can see like the unary ping pong latency in different languages on a dashboard like this. You can also see how it changes over time. Okay, so in particular, this one looks like it's pretty stable over the week that we're looking at, week of data that we're looking at. There's dashboards for this. There's also dashboards for streaming ping pong latency for many languages. There's 8-core QPS throughput in 6 languages, as well as 32-core QPS throughput in the more scalable languages. So basically the languages that don't have a GIL. We measured 32-core QPS throughput in there as well. So just again, the idea of how many messages per second we can achieve for streaming RPCs. Okay, before I go any further, any questions on what we've got so far? Okay, so like I said, these are being continuously monitored. Okay, and so this can actually help us in some ways. And we have actually used this. For example, the dashboard itself makes it easy for us to see unexpected limitations. When I gave this talk, I gave a very similar talk to this a couple of months ago at Stanford, actually, in April. And when I showed the dashboard numbers there, we were hitting about 350K streaming messages per second at 32 cores. This was way lower than what we were targeting because it's about a factor of 10 lower than what we were targeting, actually, because at that time our target has remained around 100K streaming messages per second, or about 50K unary RPCs per second per core. That actually made us wonder, we've got things are not going like what we expected, which actually triggered us to actually spend some time investigating the performance there. And one of the things they showed us was that we had problems that you might expect for highly concurrent 32-core programs, that you're likely to trip on if you're not careful, such as excessive thread hops, where the work that's being done in one thread suddenly needs to get done in another thread instead, as well as locking problems. So there are places where we did have some transport level locking and so forth that that was actually being contended, whereas it should have been contentionless. So looking at some of these issues and restructuring some of the code accordingly allowed us to push that from 350,000 streaming messages per second to 2 million streaming messages per second. Now, I can't promise you a 6x factor of improvement every 2 months. That was just, that fortunate that happened that particular time. But basically, that one of those things is that it made it very clear to us that this is an issue. We need to target it, and it enabled us to actually, do the further investigation needed to see it. Even at that time that the 350K streaming messages were going on, it turns out the latency numbers, the contentionless latency numbers, are actually still pretty good. They were still pretty similar to what they are now. So that if we just had that, one piece of data, that wouldn't have been enough. It was only when we had, these dashboards that have multiple graphs on it that we could actually start seeing, okay, what's going on here? Okay. In fact, that brings us to the next thing. You saw here a second ago that in the past week, for example, I love it when we have problems because I can actually talk about them in presentations then. Unary latency, it looks great, right? It hasn't changed. I mean, it's been very stable. Okay, you would think that this means that our performance overall has been very stable. Turns out that if you look at QPS throughput, in many languages, things have been indeed very stable. Even C++, however, C++, which we just saw the unary latency for a moment ago, all of a sudden, it looks like, it fell off a cliff a little while ago. And this is for basically a very similar test. So, but this is now, it's not the latency measure, it's a throughput measure. This is the throughput QPS. Unary RPC is still, but nevertheless, it's a throughput QPS, 32-core client to 32-core server. Still a secure connection, but we could, right away, you see, the dashboard tells us, right? We see this 30% drop. And we know exactly when it happened. It happened on June 25th between 3:45 p.m. and 4:45 p.m. Okay, that actually is a very nice thing to have because if we were only running this test once a day, we would have had we would have spent a lot more time trying to figure out what went wrong. Okay, what we know is that we can, because we know the exact hour when this happened, we can go through the merge logs and identify the suspect PR. Okay, so it's the pull request that caused this problem. Okay, in this case, the pull request that caused the problem, very straightforward what it was. It was a change in the polling strategy from using poll to ePoll, which should have had positive benefits and did have positive benefits in other parts of the system, okay, but happened to wreck the performance of this particular part of the system. Okay, as I mentioned earlier, something that looks like it will be good in some parts of the system at different levels of scalability may not always be the best. For example, if we run them on our development desktops, may not always end up having the best performance when we actually run them on our benchmarking systems. Okay, so that's the thing. So now we know which pull request did it. So let's look into what happened. So we can start looking at some of the causes through profiling, identify many of the common factors. So very common factors that have arisen a lot as you try to push the scalability, 32 cores, locking, thread hops, memory allocations, so forth. So far, most of our focus has just been on getting gRPC up and running and able to support production services. Our performance optimization, though, is going to be one of our major targets for the next 6 months. I told you one of our C++ performance goals of 100K streaming messages per second per core. That's something that's, these performance goals are very important for us, and they are going to be a major force in development for us in the second half of this year. Okay, like I said, in this case, we could identify pretty quickly what pull request caused the problem. The reason of why that caused the problem in this particular benchmark, though, is still under investigation. But we have something very clear. This has happened at master. It has not happened on a release branch. It needs to be something that's either fixed or reverted before the next release, right? Because we can't give you something that has a sudden 30% drop in performance either. The good thing about this, though, is because we're dashboarding it, it makes it very easy for us to tell, has a problem been fixed? For example, can we if we submit a pull request that we believe will fix this problem, we can see then very quickly, did it work? Did it have its desired effect after it got merged or not? Okay, we can see that and then determine if it's really ready to put in for real, or if we just need to revert the change. Okay, questions there about our commitment to performance? Yeah. I'm sorry? Erlang. Erlang. So you're using the language Erlang. It's not one of our supported languages. So our support. I understand there are community bindings for some other languages besides our supported languages, but our supported languages, the 7 that I mentioned, are C#, C++, Go, Java, Node, Python, Ruby. Additionally, we have PHP clients. So in terms, so I understand there are community bindings for some other languages. We're not benchmarking anything from the community right now. We're only benchmarking what we produced so far. Okay.
Dedicated machines? Oh, yes.
You can speak to that, Jen.
Yes. So all of these machines where the benchmarks run. Oh, sorry. Oh. Okay. Yeah. So I'll repeat that. So yeah, we do have that.
The question was, are there dedicated?
Okay, and the question was if we have dedicated machines where we run these benchmarks, and the answer is yes. We have dedicated machines in Google Compute Engine, and we have some 8-core machines, and we have some 32-core machines, and depending on which machines they are, we run different scenarios on these. Another question?
I can move on. Okay, so sorry, okay. Okay, so that's basically that's the idea and what we can achieve using this dashboard, and what how it has helped us, how we're going to be continuing to use it to help us. And like I said, it's something that you can find. It's something that we'll actually link to soon on grpc.io, but right now you can find it from our GitHub. But just to tell you a little bit about now, so we focused so far on performance evaluation. Just to tell you a little bit about where performance is going. As I said, so far the target has primarily been on functionality. In the near future, there's going to be more of an increase on actually improving performance. In C++, for example, this is our main performance target in many regards, especially for me, since that's what I have spent most of my contributions on. Right now, in streaming messages, we're about 40 microseconds above the net perf TCP/RR level. We need to have that, and that's something that we are taking very seriously. Our efforts to have that. Again, scalability as we increase to 32 cores is around 60 to 80% parallel efficiency. That number, we really feel we need to push that more to like 80 to 90%. Again, as I said before, we can look into some of the details with this through various profiling tools. The profiling tools suggest 3 basic problems that we need to deal with in a greater way: thread hops, locking, and memory allocations. Memory allocations are sort of a subclass of locking because typically memory allocations require locking. So we need to actually look more into that. Additionally, one of the things that we're looking at is providing a best practices document for programmers in C++, because of the fact that C++ gives you so many knobs to tune, and so many different ways that you can write your programs and your actual RPCs and structured RPCs. We feel that we will make sure that we have sort of best practices out there. What are the right ways to do this in order to achieve good performance? There have been discussions about this, for example, recently on questions like when to use streaming versus Unary RPCs. Streaming RPCs obviously can be done with lower latency because of the fact that they are, one continuous RPC communication. They're just pushing data and not the metadata and so forth. But at the same time, there are situations where you might end up wanting to have Unary because the Unary doesn't have state, right? For example. Okay. Other languages, C#, we are looking into, in particular, is looking at issues related to thread pool management. C++ and the C core don't, for the most part, don't actually use their own thread pools. We borrow threads from the applications, but many of the other languages do actually use their own thread pools as well. So in C#, for example, one of the major targets is to try to understand how we can better manage threading issues, as well as because of the fact that those have an interesting trade-off between latency and scalability, right? Very often, providing more threads will improve your latency, but they may make your scalability story more difficult, as well as your application-level programming story more difficult. And then moving on to the other wrap languages, I'll say that right now we basically, on the other wrap languages, Node, Ruby, Python, we've essentially done no substantial profiling work as of now. These are functional, and we have performance testing going on them. Excuse me, but we haven't actually highlighted the causes of any limitations of performance. You saw, unfortunately, some of those numbers were, noticeably higher in terms of latency of Node and Ruby and Python compared to C# or C++ or Java. And so we are investigating that as well. That's one of the goals. Now we have people dedicated to this, investigating these using flame graphs or other methods for identifying latency issues to deal with the latency concerns, as well as for the GIL languages. We are also looking at how we can improve throughput, not just by the sort of efficiency techniques that I mentioned earlier, such as that will also help us with latency, as well as just more throughput directed efforts, such as the SO reuse port extension to Linux setsoc-opt. So that's something that could also help us for many categories, not all categories, but categories of RPCs that actually are independent and can be served from independent processes. That's another sort of area that we might be focusing on. Okay, so I think there's a question in the back. Yeah, please, go ahead. Sorry. Oh, okay, very good. So the question was about what about the memory overhead? Are we measuring the memory overhead? Was that the question essentially? Right now, we're not. We're not we're not measuring the memory footprint at the current time. It's something that we could do, but right now we don't have any plan or anything along those lines to do it at this point. Yeah, that's something that we know that some users are concerned about that, and we can help them, sort of add that information in. But right now, we haven't done anything along those lines. Sorry, there's a question. Back to the question.
Do you have any
I'm sorry.
public netconf? Do you have any
Any comparison against netconf? We actually don't have any comparisons against any other systems at this point. The only external package that we're comparing against right now is netperf, just for a purpose of knowing what our speed of light sort of is. Yeah, you had a question.
Do you test on different flows?
Do we yes, all of these are tested with different numbers of channels, different numbers of outstanding RPCs. All of them are closed loop tests, so they're basically all hitting the server as hard as they possibly can. We have an open loop test. We have the ability to support open loop tests in all of our workers. That is a requirement for all our workers. We're not dashboarding those at the current time. Sure. So does this also do stress testing? We actually have a separate effort going on, or a separate effort about stress testing. So that's another thing that I can actually ask our stress testing expert to come up and speak to for a second. But in terms of trying to understand peak load, one thing that I'll say is that right now, our QPS test is sort of a stress test in the sense that we're not actually targeting a peak load right now. We're basically throwing a bunch of channels at it and a bunch of outstanding RPCs on each channel. We are probably overshooting in many cases what the actual peak would be, because in some cases it could be that we're putting too many channels and too many outstanding RPCs, more than what you would actually get peak performance at. So that's something that, in that sense, we are likely to be oversaturating it in many cases. So that's something that that's going on. But in terms of stress tests, are you talking about stability, making sure the system is stable? Yeah. So it turns So I'll get back to that story in a second. The performance testing has actually helped us in many regards with system stability because of the fact that the performance testing does push things pretty hard. We've uncovered, for example, bugs that have been latent. Like, for example, when I wrote the Ruby performance test, one of the things that came out was that beyond a certain number of outstanding RPCs at the same time, our system there needed to behave differently, and it wasn't, and so that fell over for the first time under the under our performance testing infrastructure. But now but that was sort of an unintentional side effect. But now we actually have an intentional system set up about stress testing as well. So can I bug you to say something about it? Sorry, don't put you on the spot. Yeah.
I mean, like stress testing has like distinctly different goals from performance testing, because the goal of stress testing is primarily to sort of stress the system to stress the system to basically break the system, right? To identify crashes or system stalls. The goal is not necessarily to like get a sense of the performance numbers, right? So the test cases we execute are completely different. They're more realistic, like unlike performance tests where you're like executing like scenarios primarily to measure performance, right? Like stress testing is primarily like we have a bunch of stress test executes every API that is supported in a more realistic scenario under constrained loads. So very different goals. And unfortunately, I don't have any results to share yet. So perhaps in the next talk.
Yeah, probably the next meetup. Maybe we'll make sure that happens in the next meetup. But so yes, there is a separate effort about stress testing, and that's a continuous thing that runs also. So then that's also, there's different. In some regards, some of the infrastructure is similar in the sense that all the different languages speak the same sort of proto in that case as well. But so that regard is similar, but the goals are very different. Yes.
For in your benchmark, when you're talking about Java, is it Java with the native transport or with which transport are you using for that?
It's Netty exclusively, right, that we're using for all this. Yeah, sure.
You can repeat me.
Oh, sure. The question was which transport in this Java benchmark that's being shown here, which transport is being used there?
It's Netty with NIO.
It's and so. Right. So yeah. So Eric. So just for the microphone, Eric just confirmed that it's Netty with NIO, not using ePOL.
Because we've not done like the explosion of the 5 different configurations. Like run Java. We have run benchmarks with that, and we actually we had an older benchmarking system that has that plugged in pretty easily. But for Java, we've also not done like direct executor instead of using the red bull, things like that. Just because.
Yeah. So in some of the languages like C++, we're testing more than one of the APIs. I know in C++, for example, we're testing the synchronous API and the asynchronous API. I think in Java, we're not doing all of those as well. So there's some differences, I guess, between in the levels of support in the different languages. But that's not fundamental. It's just what we're actually dashboarding at the current time. Any further? Okay. Thanks. Okay, thanks very much. Let me turn it back over to Rin.
So I think I'm next, but how do I present? Just go present something.
We should have a Google laptop. I'm not sure how it'll work. So we can.
Oh, that's a good point. Oh yeah, we can just plug it in. Beautiful.
Then.
Oh yeah, didn't I stopped presenting. I didn't leave the hang up there.
Oh, we've got an icon.
No. There we go.
Stand by.
We're good.
It's working.
Yeah, but it's not on both, so it's not recording.
Hey, Rick. Hey, Rick, can we get the picture on both screens? not sure if Rick's there.
Oh, if he's hearing it.
There's some kind of pinning thing.
Yeah, but
Is that
No, we're
this
good.
button?
You can hear it. Yeah,
there you go. There you go.
there we go.
All right, stereo. All right. My name is Eric Mears. Well, I'll get to my next slide, which introduces me. A bit about me. So my name is Eric Mears. Here's my email address. I'm an ex-Googler and also an ex-YouTuber. Wasn't sure what to write there, so I made it a Zootuber. I left Google after about 12 years to play with some different stuff, and I've always been really excited about local stuff, which is what YikYak, the company I came to, is playing with. So I had never done any Go at Google, but 3 months ago when I joined this new company, I've started hacking on Go, and so I'm still very new in all of this stuff. So just for context, let me share what YikYak is about. YikYak is very popular amongst millennials in college. Many of you probably don't know it, but if you know somebody who's in college, they probably do know what YikYak is. It's a location-based social network. Basically, it allows you to post stuff in a place and then query other things that are posted around you. So you get this kind of very local discovery and interaction, which is kind of cool. And I think that's kind of the most exciting thing, is this discovery of what is around you. That's almost like a network scan of what's on your LAN. You get to do this with social stuff and people. So system-wise, the basic challenge that we have is that there's posts that are attached to a geolocation. And when you want to see what's around you, you make a query about that geolocation. A bunch of other microservices we'll be constructing and that we have to filter out things that should be blocked for those users and so forth. But that's the basic challenge. There's a little screenshot of the app on the side here. You probably can't see that, but if you look at the feed here in Mountain View, it's probably very millennial focused. I'll say that. So what are we up to with gRPC? Why am I here? So YikYak started life as a PHP app. And it scaled up very quickly. It kind of caught fire across universities and spread across North America. It was moved into AWS and then scaled with a bunch of Redis caches and a lot of, I won't say duct tape exactly, but it was scaled to keep up with the ever increasing load. And we're now in a spot where we want to shift into a newer and more stable stack. And so we've decided to move into Go, gRPC, Protos, Kubernetes, Google Cloud, Bigtable, all these cool technologies stack. And so that's what we're doing. Our transition is just starting. We've built one service and we've just started transitioning real traffic to that. Our strategy so far, which is maybe interesting for other companies who might be doing transitions into gRPC Go, we've started with read-only traffic. So our new stack effectively is like a cache on our old stack, and we need to support our existing clients, which are all mobile apps, transparently. So we need to have a JSON and HTTPS interface. We might someday want to support gRPC HTTP2 clients directly. So we'd like to build our architecture in such a way that supports that. Although at the moment our SREs are a little bit concerned about using HTTP2 to clients. Networks are just so different around the world that makes us a bit nervous. So in this transition, we considered a couple of approaches. We considered having our clients actually transition over to use Proto gRPC. That was shot down pretty quickly. It was just too aggressive. We considered Proto over HTTP 1.1. That was something that is potentially interesting, and we might go that direction long term, but it would take a lot more time than we wanted to spend at the moment. We considered JSON over HTTP served by a microservice. Basically, we would build a binary that was that API, and then backend that with gRPC services. And last, we considered a translation layer. So we looked at gRPC Gateway or ng-HTTPX. And in the end, what we ended up choosing was gRPC Gateway. I don't have any great reasons for why we chose that over ng-HTTPX. We may go back and reevaluate that, but the translation layer is working very well for us. So just as another kind of overview, this is kind of what we're thinking. We've got this legacy LAMP stack over here on the left, and our new stack over here on the right. we're backed by our data is being stored in Bigtable and synced over from the legacy stack. And we've got this relatively simple piece of our service that's ported over. We will expand it in other ways to support other components of our API as we build them. And we've got a configuration controller that the mobile clients request a set of URLs for to do different operations. And so we can tell clients in a kind of experiment-based mechanism to use the old stack or the new stack for different operations, which works very nicely. And so what that means is that I can configure my specific phone or a region of the planet to use this new stack, which is pretty slick. Our flow goes from our clients, which are mobile apps primarily, although we do have a web app, through JSON over HTTPS. We run through an NGINX proxy, an Nginx, I think is how you say that. And then that thing continues to talk JSON and HTTPS to our front ends internally, where our gRPC gateway terminates that. And then we switch over to all Proto and gRPC at that point. And then make requests through our feed service, which is basically collecting together a set of posts and doing operations on what we want to feed our users, to our geo service, which does smart querying against our Bigtable that does these actual performant geo lookups of posts that are relevant for the users. More stuff to come. We have a lot more work to do. Okay, so as we're still working on this stuff, I wanted to share with you guys just some challenges and snags that we've run into using this new stack. So I've got two examples. One was that this is just me being a noob. This is not like a flaw in anything. This is not going to be insane insight. So we were using gRPC gateway, and it was challenging for me as a new Go programmer and gRPC user to figure out how to get our HTTP headers as well as other data into our gRPC stack. So it turns out it doesn't happen magically. You need to do something special, and so I wanted to just share what that was in our particular case. So in our, it turns out that that gRPC gateway does magically transform headers into metadata context. It does this if you have a prefix on the header. This is something that could potentially be a security issue if you were not aware of this. But anyway, if you prefix something with if you prefix a header it's sent into gRPC gateway with gRPC-metadata-something, it will show up kind of magically in your metadata context. Although it's worth noting that there are some magic headers. gRPC-metadata-host breaks in some reasonably spectacular way because it collides, I think, with the host that gRPC is trying to set itself. Maybe, not sure exactly what's going on there, but that doesn't work. So watch out for that little pitfall. And then lower down, I've just got a little example of pulling out of context, which is not a particularly exciting thing. Although I'll take an aside and say that context is really cool as a part of gRPC and Go. I've only used gRPC in Go, so I'm not sure if context is like a Go thing or a gRPC thing, but it's very cool. Another snag / challenge here, load balancing. So gRPC is great to make a connection that's stable. It will reestablish itself if it breaks, but typically the connections are long-lived. And this is a little bit of a problem if you scale up your service and you end up with new downstream backends. Your front ends just don't magically find them, which also is kind of a new problem, I think. So we've identified this issue as we tried to do scale ups of our service under load tests, and we found that the new backends just don't magically appear. So there's not magic there. We played with some server side, or some client side pooling. So we would create a pool of connections, and then when we wanted one, we would pull it out of the pool, and then we'd have a Go routine that cycled that gRPC connection, cycled it out of use. That basically worked. It was functional enough, but it added a lot of complexity. And what we found for the stage that we're at was that because we're running all of our services on a data center, and everything is very close network-wise, it was just simpler to use a dial on every connection, which does feel like a little bit of an abuse of gRPC. And I think we'll come back to a more sophisticated mechanism in the future. But for now, this made a lot of sense. yeah, so that was kind of the keep it simple approach. So some things from my experience as a new developer about the stack. Super fast to compile. Everything is really fast. It's really stable. Generally, things work really well. Protos are great interfaces between things. It's pretty amazing to use protos versus kind of, you know, I went back and I needed to look at some JSON interfaces over HTTP, and it was just a pain in the butt to have to work out both sides of the interaction. And protos are great for that. The context and error passing stuff in the Go gRPC setup is amazing. It's very cool that you can see an error that starts low in your stack and gets populated up to the top. The only challenge I've run into, and this is certainly a user challenge, is that it's a little bit hard sometimes to figure out where the origin is, because you'll see the same error populating through the stack. So I think we probably need a convention for indicating where there's an origin of an error. That is the first place that's surfacing that. Call cancellation is also super cool. So you can do all of this great stuff where you're making calls to many services, and if one of them comes back and is an error, for example, we've got an authentication service that we call, and if the authentication comes back failed, we can cancel our other requests. This of course makes sense in a read case. It doesn't necessarily make sense in a write case to parallelize your operation with your authentication. But it's very, very easy to do this in Go and gRPC, and it seems like it's quite efficient with call cancellation. So what's next for us? We're building a lot more of our stack, moving out of this LAMP stack, building for parity, as well as some new features. We're battling with our PMs a little bit about how much new stuff to build before we're off of our old stack, but it's a normal and natural ecosystem of PM and engineering. I'm personally really excited to play with gRPC streaming. At the moment, we're not doing that. We're making discrete calls. I think that'll potentially be very cool for our service to be able to stream results directly to clients and then have them resort. So you get this sense of very, very fast, very low latency, but still be able to have relatively long running queries that give you very, very good results. I'm just having a great time coding in Go and playing with gRPC. And we happen to be hiring in San Francisco and Atlanta. So I was way under time, but that's my presentation. I'm happy to answer any questions if you guys have them. Yes, sir.
So what was the issue with HTTP2 with your clients?
Oh, what was the issue with HTTP2 and clients? The issue is mostly that we don't necessarily trust the rest of the internet to deal with HTTP2 properly, as well as debugging and yeah, if they're behind a NAT or a proxy, we're mostly paranoid, perhaps. It's hard to test the whole internet for a small company, and so given that we have existing HTTP 1.1 clients that are working well, we don't want to change too much stuff. Although personally, I'm excited about transitioning to HTTP 2. Yes.
Are you on TLS for the requests, or like especially like the reads?
Are we forwarding TLS? Not at the moment, but we probably will be. Yes.
So I didn't catch that realize that this tools, but you're using gRPC for communication in your mobile app and your backend.
No.
Between your microservices.
So we're using gRPC for everything but our client to front end communication.
That was your I mean, you would want to do so. But yeah.
The question, sorry, what is your question?
Yeah, in a perfect world, you would want to do so, but you don't do that for
The question is, why don't we use gRPC and HTTP2 to the client? Yeah, it's basically the same answer, is that we're mostly paranoid about not trusting it because it's too new and cool.
you would be open to that.
I'm personally very excited about it. Our SREs who should be paranoid about things like that are paranoid about them. Yes.
One thing that is very interesting in Go is this debug
Are we using the debug args interface? Debug request. This is the one that gives you the picture of your call trace? I've seen some of those graphs. I've not created any of them myself yet, but I'll dig deeper into that. Yes.
Sorry, I have to ask a newbie question because I'm not a millennial, so I haven't figured out. So is your system on web as well as mobile, or is it strictly mobile?
It's primarily mobile. You authenticate on mobile, and then there's a mechanism to basically use the app, use the same interface on web.
So
but
is that a limiting factor for not being able to use gRPC to the client, and also because of the fact that right now
it's a consideration. Sorry, the question is our use of both web and mobile a consideration in not using gRPC as the client? It is a consideration. We could potentially have a gateway from, if we primarily had a gRPC client, then we could imagine a gRPC client that then serves web. But at the moment, even to mobile apps, we're just being, we want to change fewer things at the same time. Yeah. Yes, sir.
Do you use any service registry to discover services?
Sorry?
Service registry to discover.
A service registry. No, we don't use a service registry at the moment. We have things configured by command line. Yes. Go is the only language we're using it with gRPC at the moment. Yes.
Using Kubernetes for your service.
Yes, we're using Kubernetes. Yeah. All right, I think we're out of questions. That's it. Thanks, everybody. Who's next? A break is next. All right. How long is the break, Varun?
So we'll break for a while, and then
All right.
we can break for 5 minutes. Let me see the time. You were in time, so we have
I was
extra 5 minutes of break.
all right.
So 15 minutes.
15-minute break. Fast forward 15 minutes.
There
you are. Thank you.
that's my interpretation of why they said that. Why they started with it. That's my interpretation. They didn't want to give us any
Should be just straightforward.
What is it showing us instead of?
You need to. Are you presenting already?
Yeah. I mean, I can see the second screen here.
Maybe you want to drag it.
There we go.
Yep.
Everything that we run, including our Docker files and everything, we're all on our GitHub. Everything. We're not doing a single thing that is.
Do I need to do anything else?
We have. It was not. It wasn't as much as we targeting as well as the abilities that our team has. But we also have. We do have some of our team members has there are Haskell bindings. So I know that there's some bindings. I know it's not functional, but we're on we're not supporting it. But basically, what you're There's a question about C API. So, yeah, I Yeah, we are still speccing it out. It's a lot of work. Speccing out the CAPI. Yes, except the okay, assuming you have a so we have a couple of options. It's not like the official so you can generate so and not all the language features might be supported by language. So let's say there's like one of I don't know how much you know so for the basic features you'll be fine. You might find some places where let's say some features that get recent to product 3 might not be supported by language. So that needs to probably in your messages you might need to basically help users. So that like support for messaging. So I have checked, but I assume that none of these don't have yeah, so for and depending how complex the protocols are, you either not running notice. And if you have like the big protocol business, you might actually find out
so I see that in the gRPC repository like this has more and then has a lot of we have like the server
yeah. So I mean, that's obviously a public CA, but that API is not intended to be consumed by like any users. So it's not community. So it's actually an implementation of gRPC in some language. You can use this to actually cover that. So like that API is part of slow. It also creates like a rectangle. And then never came back. API, we have languages to rapid definitely not a good idea. So you did the right thing by not using it. Because I moreover, that has no notion. There's no notion of payload. Payload. They just do it. It was the case I yeah, so and this is what we done for like all the other Squatter will do all of that. Couple of and then I think I mean, that's like probably have something that people have to buy. There's so many scenarios to cover. Security stuff you haven't looked at. So even finalizing the API, nano maybe people I haven't been I haven't looked at it, but DeFi was saying that nano maybe it's a lot of things to do. Something is the payload API. That is what that is Android. I mean, it has been done like 8 times. Just about figuring your right question. I'll probably write Python because I know.
All right. Shall we? Hello, 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 hello. All right. All right, let's restart. All right, guys, let's passionate conversations, hard to stop them. Needed beyond, I know. It's a small one. Is there something I need to switch on? All right. Hello.
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 That works.
That might work. All right, I know this deep, passionate, interesting conversations, but we have a time clock ticking and don't want to cut on Benoit's time.
I still
So
need to
if we
use
can
this,
get-
right? Even though it's working.
That should-
Hello? Yeah?
Yeah, it works. All right, so if we can get seated back again, and we'll get Benoit going on the interesting topic. I met a few people like, we came for this talk, so no pressure.
All right.
All right, with that, Benoit, take it away.
Thank you. So hi, everybody. I'm Benoit. I'm on the software engineering team at Arista. Arista is a data center switching company. So we basically sell switches that go in data centers. And today I'll talk about network state streaming with gRPC. So what is the problem that we have with network monitoring today? The problem is that this is basically how network monitoring today works. You have a device and you go over some protocol, typically SNMP, and you ask the device, nope. Yeah. Are you okay? Are you okay? Are you okay? Like every time you have to poll the device, constantly asking the device, how about now? How are you doing? Are your interfaces still up? How about the counters? What changed? So you always have to poll the device all the time. And that's really annoying because when you start scaling the devices and you have thousands of interfaces in them and lots of state that you want to collect, scraping the entire state of the device all the time, especially if you do it with an inefficient protocol like SNMP, is, well, pretty inefficient. So this has been a theme for me for a while, which is always trying to twist this thing on its head and asking the system, why don't you tell me when something changes, right? I want to monitor you. Why do I always have to go ask you how you're doing? Why don't you stream to me what's happening? And so actually I was at Google a few years ago, and after I left Google, I implemented an open source monitoring system called OpenCSDB, which also revolved around the same idea, which was that instead of having your monitoring system collect the data from the systems that it's monitoring, it's the other way around. It's the system that it's monitoring that should push and stream the data to the monitoring system. And that's a lot more scalable. It's a lot more efficient. So why don't we do the same thing for network monitoring? So state streaming. Network management hinges really on two things. You want visibility and control. You want to see what's happening in the systems. And then once you see what's going on, then you can exert control on the systems to make them do what they should be doing or react to things that are changing. So streaming telemetry is really important to provide this fine-grained, real-time visibility that you need to be able to exert this control using APIs. So you need this to do monitoring and alerting, but also real-time analytics and just to like react to changing conditions in the network. So streaming is all about having these continuous streams of notifications to tell you what's changing and how it's changing. You don't want to be polling the systems. Okay, so now a small parenthesis on the history of the network industry. So the network industry for a long time has been using some sort of like a big switch which is pretty much like a black box with an embedded system on it. And over time, all of the systems have evolved to more modern operating systems, usually running some sort of a modified BSD or modified Linux, to the point where today the switch is just a Linux box. Just like the phone in your pocket is a Linux box if you run Android, or a Unix-ish box if it runs as iOS. The switches today are also all becoming Linux boxes. All the vendors out there, they're all moving to Linux. So you can start thinking of a switch as basically just a server that has more advanced networking capabilities. And that's what we do at Arista. Like we have this EOS, which is operating system, which in fact is just a code name for a Linux distribution. And on the hardware side, also, like you no longer see a lot of custom hardware. It's it's the big chip vendors or chip makers that make the modern hardware. So if you look inside of a switch today, like if you crack open the switch, which would void your warranty, you see something kind of like this. You see a bunch of power supplies, PSUs, some storage, some DDR, and a x86 CPU. And then you have a network chip. So this is very much like a server, and it runs Linux. So really like think about switching software and switching systems as just Linux systems that have more advanced networking capabilities. So it's all about the software, right? Again, it's like, whether you like Android or iOS, well, it's because of the software. Do you prefer this set of software or that set of software? So that's mostly how you decide. And you can plug in a lot of open source software on top also because, well, it's just a Linux box.
You can script it, you can program it, you can extend it, you can install any existing package on it. That's great. So closing these parentheses, now if you think about the network as basically a set of servers that run Linux that you can extend and query, why can't we also do on the network what we do today in monitoring infrastructure, which is what I was doing with OpenTSDB previously, which is to say, I don't want to go to all my monitoring targets and always ask them, hey, how are you doing now? How are you doing now? I want to twist this thing on its head and have the monitoring target report to me what its state is. So enter state streaming. So we started building a prototype a little bit more than 2 years ago. And that's roughly how it looked originally. So we have our switches. In our switches, we have a component called sysdb, which is like our in-memory database. It's a little bit like Zookeeper or etcd, if you're familiar with this. It stores the state of the switch. And we created a telemetry agent that can stream the state of the switch to a distributed backend. And then on this distributed backend, you can access that state, write applications that react to that state, that exert this visibility and control. So you stream the state updates, no internal polling whenever possible. That's great. And then in January last year, we got in touch with, or rather the gRPC team got in touch with us, Giant over there, and team invited us to get a preview of gRPC, and we were pretty interested because one of the big annoyances that we had in our previous prototype was using HTTP. So when you use plain HTTP is pretty much unidirectional, right? Like you have a client sends a request to the server sends a response. It's hard for the server to like proactively push back things to the client and have bidirectional communication. And so one of the initial strong appeals to us for gRPC was the bidirectional aspect of gRPC, because it runs on top of HTTP2, which is a bidirectional streaming bidirectional protocol. So a few months after meeting with the gRPC team, we started to build a new gRPC codec, and then we started to migrate our ingest layer to Go plus gRPC. And on the back end, we're still using Finagle. So for those of you who don't know Finagle is the framework on top of which Twitter runs. So like all of the Twitter services and microservices, not all, but like the majority of them are written using Finagle, which is a framework in Scala. And so that's what we started with also. Finagle is a great stack. I love it. But in the end, we basically ended up rewriting everything in Go to the point that now we no longer have anything running on a JVM. So really the goal for us was not so much to get rid of Finagle as much as it was to get rid of the JVM. So now we pretty much have gRPC end-to-end. And there actually should be a couple stars there. One is, well, except we don't speak gRPC to the browsers, obviously. And also, we don't speak gRPC to the third-party services. Like, we run Hadoop, we run Kafka, Elasticsearch. So all of these use different protocols, which is a little bit annoying because you cannot do end-to-end request cancellation easily when you have these kinds of other services that don't speak gRPC. Anyways, so state streaming, using gRPC, and then changing our backend over to using gRPC also for the communication between our different backend components. Now I want to talk about another thing that happened in the meantime. So again, this was like over the span of the last couple years. A little bit more than a year ago, maybe a year and a half ago, there is a new movement that started called the OpenConfig Working Group. So what these guys are doing, it's basically a bunch of large operators like Google, Facebook, Microsoft, Comcast, AT&T. They got together and they are trying to build a set of data models to be able to interact programmatically with network elements in a vendor-independent fashion, so that the way that you input the configuration in an Arista device or Juniper device or Cisco device is the same across all the vendors. And we're pretty excited about this effort because, of course, the vendors never agree on anything. So if it comes from the customers, then the customers can impose a set of standard protocols to use. Except that OpenConfig is more about data modeling than about protocols. So SNMP so far was like the sort of de facto standard protocol for network monitoring. And SNMP is, as I said earlier, you're like, are you okay? Are you okay? Are you okay? You're always polling the devices all the time. And it's pretty inefficient. So instead now with OpenConfig, one of the goals of OpenConfig was to enable also a pub/sub model and streaming telemetry. So we've been working pretty closely with Google also on this one, on the spec and implementation. Our implementation as well is in Go. And in the OpenConfig world, basically, if you look at the different large network operators out there, gRPC is basically the newest option on the block. There are two existing protocols that have been used in the industry before, RESTconf and then the other one, netconf. And in my opinion, gRPC is the best protocol because it has this bidirectional streaming aspect. It's based on HTTP2, which is the new standard for the web. And it's the most efficient transport mechanism based on protocol buffers. So we started to implement OpenConfig, and as I said, we also had our existing telemetry system, and we unified them so that they use the same gRPC interface. So you can basically access our devices using the OpenConfig data models or using our own data models, both using the same gRPC interface. So we're very happy with gRPC overall. We've had a great experience with it. It's been working great both for streaming telemetry and for our backend systems. Now it's not, all perfect either. So first, the good things is what I mentioned. So the fact that gRPC is based on HTTP2, that it has bidirectional streaming, it's fast and secure, using compression and TLS by default. One really important thing that gRPC got right from the get-go was end-to-end request cancellation and deadline propagation. This is really important when you start building distributed systems where you have microservices that talk to one another. So like to serve a request, you need to talk to another backend service, which itself needs to talk to another backend service. You need to be able to propagate the deadline of this entire tree of requests and the cancellation. Like if the input request is canceled, you want to cancel all of these subtree of requests. And gRPC got this right from the get-go, which is not very common in RPC systems. And even though for the projects that I mentioned, we basically ended up converging everything onto Go, we really like the fact that gRPC is polyglot. We have some people who also want to use Python to talk to our systems. And so even though the Python support is not quite there yet for some things, it's great that you have all of these languages available. Now, some of the pet peeves we've had with the Go implementation specifically, it depends on protobuf 3, which has been in beta for like more than a year now. So when people want to compile stuff from scratch, they have to install this development version of the protocol buffer compiler. It's not the end of the world, but it's kind of a barrier to entry. Load balancing has been nascent, so there has been some recent changes that merged for load balancing support, but it's still not quite there yet. But not all it doesn't really come with all of the features that we expected. And in this respect, I want to talk about a couple of things or a few things we missed from Finagle, which is the framework that we left when we moved to gRPC. So one thing that Finagle does really well is making services composable. So you can basically take one service and like pipe it into another service and pipe it into another service and like have this all be into one process. So it allows you to basically layer your business logic in different layers that you can very easily plug into one another. So filters and services are how you do this in Finagle. You can have these different modules that you can then put together in a pipeline. And that's not something that you can easily do with gRPC. Another big problem for large-scale production systems is the lack of explicit queue management. So leases, negative acknowledgements, back pressure signaling, these things become really important. And somebody was talking about stress testing earlier. These things become really important when you have large-scale production systems that are under duress, whether they are because they are attacked or just because they are overloaded. So for those of you who don't know what these things are, basically the idea behind a lease is that when you connect to a server, you cannot send an RPC to the server until the server grants you a lease to send a certain number of requests. So it's like, hey, okay, I'm gonna allow you to send me 100 requests, and once you send me 100 requests, you have to ask for more, and I'm gonna allow you to send me more. And so basically, the server can pace the clients. So if the server is overloaded, it doesn't give any leases to the clients, so the clients cannot keep sending requests to the server. And that's a very good way of doing back pressure signaling. If the server is too busy, it's overloaded, or it's self-blocked because one of its downstream services is blocked, it's a very good way of relaying this back potentially all the way to the clients. Other things we missed from Finagle, a mature RPC tracing framework So gRPC is very extensible, has a lot of hooks that you can plug in. There is some form of support for RPC tracing, but there isn't like a turnkey solution that does end-to-end RPC tracing, collect all the traces, stitch all the traces together, or show me the call tree in my backend services. So all of these things are just due to the fact that Finagle has had more time in production than gRPC. They are coming to gRPC, I'm sure. I'm not privy to the gRPC roadmap, but I would imagine that they're coming. So yeah, I just wanted to name a few of the things that are important for production large-scale deployments. More metrics. So yeah, you can get a basic latency histogram, but there are a lot more metrics also we would like to expose. So right now we expose these metrics ourselves in our code. Other things also like RPC logging. I want to be able to like log RPCs to a file, be able to like look at these files, inspect them, easily replay them. So when you want to do a load test of your backend systems, the best way to do a load test is to actually capture production traffic and replay the production traffic against your backend systems as quickly as you can. So these are some of the things that we miss. So we love Finagle, but the reason that we moved away from Finagle is mostly because we wanted to move to Go and stop using the JVM altogether. Now, in terms of wish lists, a bunch of things, but ironically, the number one thing that keeps coming up over and over again, and that's not really from me, but from other people at Arista, is to be able to use a gRPC interface directly in the browser. So like have some sort of a built-in browser compatibility or browser support so that a browser could connect to a gRPC endpoint, ideally with HTTP2 if the browser is HTTP2 capable. Otherwise, use WebSocket or something, an approach similar to what SubJS does on legacy browsers to degrade to some other kind of bidirectional streaming mechanism. So that we can easily build applications that for the web that plug into gRPC servers. Right now we have just these API servers, which is what Eric from YikYak was mentioning earlier, that do the translation between JSON and gRPC. So yeah, I guess that's pretty much all I had for you guys. I would like to open the floor to any questions that you may have. Again, this was a really quick presentation. Thank you. Any questions? Yes.
So HTTP2 has something similar to this. That doesn't work. There's a server says to the client, you can send me this number of bytes.
Yeah, I don't know of a, like, how do I do this with the gRPC API? Like a. So the question was, sorry, I'm going to repeat the question for the recording. The question was, well, HTTP2 has some form of leasing support. Why can't I use this? And yeah, so I was saying, like, I don't know how to do this with the gRPC Go API. Maybe I just missed it and it was there all along. Like there is no way for my application to convey this, as far as I could tell, like to signal this to the transport layer.
One the server, let's say,
it is a form of flow control. It is a form of flow.
So you care about this actually end-to-end or...
Well, no. Usually it's hop to hop, and it ends up doing end-to-end flow control. If one guy is blocking, it will end up blocking the next guy, which will end up blocking the next guy. So it ends up being end-to-end indirectly. But like there is no way for me to say, I'm going to give you a certain number of credits and you can talk to me this much with these credits. And then if I'm not giving you more, you have to go talk to another instance of this backend, right? So it kind of ties also into load balancing because usually you connect to a bunch of backend instances and then you get a bunch of leases from them. And then you can only talk to the ones that give you some leases. This is something that is in Finagle. So Finagle has a transport layer called MUX, which basically allows you to do this and more, which I think gRPC and HTTP2 is basically the same, does a lot of what MUX does for Finagle, yeah.
HTTP2 does have max concurrent streams, which gets you something close. It's not quite this.
Max concurrent streams in HTTP2?
Yes. For what you're talking about, there would still need to be more APIs.
No, but like, so the idea is I can connect to all of my backends, but just because I can establish a connection does not necessarily mean that I am allowed to send any requests to the backend, right? The backend has to give me certain credits so that then I can talk to the backend.
Right, and so this would be pretty similar, but we need to give you more control.
Yeah, because it has to be something that I can control at the application level, because my application, for example, one of the things that they did at Twitter that I personally have never done with Finagle, but makes a lot of sense, is when you know you're going to do a GC pause, you just stop handing out credits. So like people don't talk to you. You go take your GC pause, nobody's talking to you and seeing that your latency is going to shit during the GC pause. And then once you resume, you can start handing out credits again. So that's something that is completely decoupled from your any queues or any the pace at which you serve requests or whatnot. It's just you have some sort of a application specific thing that says, now I'm going to stop for this reason, which is completely arbitrary. I'm going to stop serving requests, and the way that I stop serving requests is that I just like stop handing out credits, so people stop talking to me. Yeah. Any other questions? Yes.
If your application is lost, it can talk to gRPC, right? What's preventing you to write?
If my application is in JavaScript, it can talk gRPC. Well, I'm not aware of any gRPC client in JavaScript. Well, yeah, in Node.js, but not in the browser, right?
Yeah, the issue with the browser is we need to have a browser expose a API to the JavaScript page. And right now, there is a proposal for Fetch API, but there is no browser which has support.
So Giant is saying that there is a lack of API to expose the HTTP2 capabilities to the JavaScript layer in the browsers, which is why there is no JavaScript gRPC client in the browsers currently today. Yes, question. Sorry, I didn't get the question. With a Chrome extension, would it be fine? No, I don't think so. Like, I mean, for development, maybe like if you have a development dashboard and you can assume people on your team use Chrome and install the extension, maybe, but otherwise it has to be a mechanism that works in all browsers and that degrades also with other browsers. So I mentioned SockJS is a library that enables bidirectional streaming. It will fall back to like creating frames, I think, if you use like an old version of IE. So there's at least two different mechanisms to do WebSockets. There is XML HTTP request. There are a bunch of different mechanisms. So like SockJS is a library that abstracts this away and finds the best mechanism that the browser supports to do bidirectional streaming. So it's just a JavaScript library that you can. And we used to use SockJS also in our previous implementation. Now we're just doing WebSocket. But yeah. So I think a solid in-browser gRPC implementation would have to support also legacy browsers that don't have HTTP2, that don't have even a good WebSocket implementation, stuff like that. Yeah. Yeah, I want to be able to like serve a web page to a customer that has a web application that communicates to my backend with something that on my backend is just gRPC. Yeah.
How important is bidirectional streaming?
It's critical. The question was, how important is bidirectional streaming? It's critical. I mean, if you don't have, like, that's the whole appeal, right? Like, and you write a gRPC. Like you write a gRPC interface, often with some form of bidirectional streaming. So if you can't leverage this in the browser, it greatly diminishes the value proposition of gRPC. Yeah.
No, there's an ongoing effort, some JS library, but with all the constraints that Jen mentioned for server streaming.
Yeah.
So that's something which will be usable sooner than full execution.
So there is something that's coming that may not have all the, I'm just repeating for the recording, that may not have all the bidirectional streaming capabilities, but something is better than nothing. I appreciate that.
server streaming direction is
Yeah, the server streaming direction to the client is easier, obviously. All right. Any other questions? Well, thanks, everybody.
So, this is schedule-wise, this is a wrap, but we have heard a few, we'll take 5-10 minutes maybe. If questions that you came with and you didn't ever get a chance to talk to someone or ask them, and this, we don't want you to go away without, having had a chance to ask them. So I just wanted to have the floor open for a few minutes if somebody had. Okay.
So I'm not working on gRPC team, so I'm curious actually how many people try to use gRPC from their apps?
Mobile apps?
Yeah, mobile apps from iOS or Android. And what was your experience? And what was your experience, or what were the problems?
Anyone wants to go with? Okay, we have.
I don't know. I mean, I know that there are mobile applications.
So he comes from Nest, so you can talk.
I can, if you want, I can connect you.
Yeah. Anyone else? Mobile apps? Yeah, Sandeep.
I work for Google, but we don't work on gRPC, right? We did it on Android, and it was fine. It's just Java.
I can speak for mobile games at Google.
Okay.
I work with people doing iOS apps.
These are all internal. You can talk to them.
I see.
You had. Did you raise your hand on mobile? Okay.
No problem.
Okay.
Yeah, you might talk to the two of us.
Yeah. Okay. Was there any other questions before? So, anyone going once, twice? When is the next meetup? That's a good question. Not on a concert day. Probably not in this building, which is restricted everywhere. So we have more public access. So we don't have a date, but the plan is to do this every other month. So hopefully in August or how when. All right. So I think if no others, that's a wrap. Thank you so much for coming.
gRPC stickers.
Yes, I have.
gRPC log, by default, it just goes to standard error anyway. So gRPC log goes unless you set